Not nice about that. Okay, so welcome to the second half of today's lecture, right? Again, we are doing big data analytics, and this second half, I'm going to actually be talking about basically the science of doing data, right? Why makes it a data science? Okay, it's not just a fancy name for somebody who punches, do a lot of computation on do regression and some kind of data pivots and graphing and all that Those are all technical little skills that are important, but that does not make it data science. Okay. So let's go. There are three aspects to this class. The whole thing is about data analytics. The whole thing is about data analytics. And the tools that are needed are basically statistical methods and machine learning. And like I mentioned, as I mentioned in the earlier part of today's lecture, I'm going to be assuming a lot of knowledge here, okay, from your year one exposure. But I will be touching up or sort of like reviewing and expanding on some of that. But I'm going to assume you don't know anything about machine learning. So I will spend a lot more time, a substantial part of the time on this. Okay, so let's go to data analysis. What are we talking about? Well, make it a little bit bigger, right? So let's talk about data. What do you mean by data? Let's talk about analysis. And let's talk about data analysis pipeline. That's something that will become more meaningful as you get more like hands-on experience. But in this class, it's not about experience building. It's sort of like, it's about trying on for size, experimenting, just playing around with a baby problem. Okay, so the baby problem will have a very tiny, a very nice data analysis pipeline. A big problem will have a big and complicated pipeline. But the concept of doing analysis from end to end will be introduced here in this course. Okay, so let's talk about data. Okay. What do you mean by data? Okay. By the way, I tend to do a lot of this. I tend to do a lot of fundamental definition because a lot of time you hear words and buzzwords in the media or in whatever, YouTube, and you think you understand it, but you don't really understand the fundamental ideas or the concept. So I tend to go back to basic quite a bit, okay? In the beginning of the class. Go down to the definition. What exactly do we mean by this? What exactly do we mean by that? What are we trying to do today? Okay, and then when we go to the technical part, I'm going to go to the technical part, run through the algorithm, but I would apply on a very tiny problem that in actuality you can probably figure out in your head. Okay, but I would use it to the full machinery of computational machine learning algorithm just to show you how it works. That's it. Okay, right. Let's get started. Definition. What do you mean by data? Well, in order to be a data, it's a result. It has to be a result of something. It has to be a result of some kind of measurement process, some kind of records keeping. Okay, it has to pertain to something specific. Specific what? It pertains to specific sample of entities or series of events. Okay, it's very important. If you have a complete record or complete enumeration of possibilities, that's not data. Okay, that's not data. Okay, so in a way, chess moves are not data because you can enumerate all of them theoretically. Now, the reason you can't do it is because the combination is so big. So you actually have a database of historical chess moves. But technically, if the chess combination of chess moves is small enough, okay, you can enumerate all possibilities. So it has to be, data has to be a measurement. There has to be a limit. It cannot pertain to the all population in our case, okay? Now, you can say there's such thing as a population data, okay? Like you can have a population consensus data. That's also data. But in our context, chances are you're not working with that, right? So if you want to know about, say, the health of a population, you have to predict, you have to model. But if you already have a register of the health status of all 70 million Thai people or 8 billion people on earth, okay, that is also data, but not in our case, okay? Data for analysis, somehow you have to work with unlimited data. It's not knowing everything about everybody, okay? So it's not the universe of data. It's the data that you can have access to. And that's always specific. There's always a scope. There's always a scope. This data was collected on Thai female students between age 18 and 25 in 1989. It's always it's quite specific, okay? Or this data set is about time series prices of Thai stocks between 2000 and 2020. Okay, it's always limited. You don't have access to future data. Okay, but that's obvious, right? In time series. But this is very important. There's a limit. There's always a limit. There's always a scope. However, there is a general population or phenomenon that you are referring to. So you don't have numbers on everybody in the population. You have numbers, records, measurements on a sample that is reference to the population. Okay. So just now I was talking about a sample of what? Thai female students, blah, 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 blah. Well, that is reference to all Thais, all females, all Thai female students of any year, any age, or something like that, okay? Or in the present, not just in 1989. But we have some job because we don't have information on everybody. We have information on just a subset, on just a sample. We want to analyze. Why do we want to analyze? Because by analyzing the sample, you get insight about the population. That's the entire name of the game. Okay? So data is not just about record. If data is just about record keeping, and you can keep record for everybody on earth, you don't have to study data analytics. Okay? Well, actually they do. There are actually difficult problems with that too. But for this class, let's say for this class, let's limit ourselves to the case where you have numbers, data that pertain to specific sample, reference to the whole population. And you want to analyze the sample so you can understand the sample, but your understanding does not pertain to just that sample. You have to understand this so that you know about the general population. Okay? So that's very important, okay, from our part. Now, what kind of form and format? Well, I'm going to say that most of the time, let's say 95% of the time, 9 out of 10, whatever, you are going to be dealing with some kind of tabular data, meaning tables. Now, what do I mean by tables? Think Excel. Just think a spreadsheet. A spreadsheet has different columns, and they refer to different attributes, different records, different measurements, and they have different rows. And those are individual samples. So because it looks like a table, we call it tabular data. Okay. Now, and this is where we start to look at real data, you would see two kinds of data. In fact, you can record two kinds of data, right, on Excel. So let's say I have an Excel. Yeah, doesn't matter, right? So you can say this is Alice, A, let's make it Alice, B, let's make it Bob, okay, C, let's make it Chris, right? And you can say something like height, okay, 1.7, 1.8 meters, and 1.56, whatever, right? And zip code, okay? So as we said, well, this whatever, doesn't matter, I don't know. Yeah, zip code and color, hair, short, long, short. Immediately, right away, you can see that these are different kind of items, right? These are numbers. This is a number, but actually it isn't. It's a name. This is also a label, right? Long, short. So you could have two kinds of stuff. You can have descriptive, categorical. You can have quantitative, like numbers, numerical. So let's separate that further. Now I'm going to reference what's called number scale. Number scale is the single most important thing not to forget, because even seasoned data scientists make a mistake when they mix number scales. One, remember data is about measurement, right? Measurement against what? Well, when you measure, you always have to measure against some kind of scale. So there are two kinds of scale. This scale is called nominal scale. Okay, come from the word name. Okay, so let's go to eTIM online. Go to the word nominal. Okay, pertaining to nouns, pertaining to names or name. Okay, nominal scale. What it means is that it's used to name things. Now, can you spot which one are like that in this example? Obviously, the zip code, right? 10110 is just a name. Okay? You know why it's just a name? Because you can't do something like this. It makes no sense, right? You have three people, you have three friends, and you say, oh, you know, what's the sum of the zip code of all my three? It means nothing. 3228 doesn't mean anything. It absolutely means nothing. Also, what else doesn't mean anything? You can say that this one, subtract this, is equal to 7. What does that mean? Does that mean this area is better by 7? No, it doesn't, right? It's just a name. Literally, it's just a name. Now, originally, it could have some sequence of meaning, like your student ID. Okay? Your student ID, okay? Presumably, okay? Presumably, I have this person who is 80040 and this 80056. It does make sense that 56 is bigger than 440 and 107 is equal to 56 because that's the order that you guys register, right? But am I going to use that as a basis for grading you? No. Once it becomes your name, that's all it is. Oops. Student roster, like that. Okay? Once it becomes a name, it means nothing. So, what can I say about nominal scale? Now, if you took my summer course, pre-math, you would know that we can subject this to an operator, a Boolean operator. that Boolean operator is equal. Right? So I can say that. I can say that. And this one, is it equal to that? False. So a nominal scale, what operator can you put it, can you subject it to? Equality, inequality. That's it. Equality means same. Inequality means not the same. But this is not equality in terms of performance. This equality is more than that. When I say A is equal to B, I don't mean that A is of the same size or anything. I'm saying that A and B refer to the same thing. Okay? So if your student ID matches student ID that does this and student ID that does that, if it matches, it's not saying that there's some quality that is the same. It's saying it's the same person. Yeah, that's it. That's all you can do. Now, what else does this number suggest? Now, what if instead of having this number, I have something like a grade? Okay, so Alice is in 7th grade. Bob is 9th grade, and Chris is in 8th grade. Now, can I say that somebody is higher? Okay. Now, this is a little bit more than I wanted to say. So let's say something like, well, let's do this. Let's do this. This is the eldest. Let's say Alice is nice. Not nice. Very nice. Okay. Is this a name? Is this a name? Does it define identity? No, because you can have David, who lives who also nice. Okay. Now, is nice here equal to nice here? True. My question is Alice Bob? Is Alice David? Alice is not David. So equality here is an equality of attribute. Okay. Now, what else can you do? Well, in theory, you can compare because you prefer nice, very nice is better than nice, and it's better than so, and it's better than not nice. Can you say that? Right? So this is what is called ordinal scale. Okay? Ordinal scale. You can do this. You can do this. But what you cannot do is measure the difference. So all you can do is this. Greater than and lesser than, right? Okay. So you can do the above and you can do this. Okay. And you can also do, greater than equal to. That's it. That's all you can do. This is very important to basically have this mental awareness of what you can do with your data. And this, again, I'm going to keep hammering this down because seasoned data scientists, in my team, not very close, get this thing mixed up all the time. Okay. So that's it. We have that. What else can you think about greater than less? This is something like blank. Okay. Okay. So maybe I can put this. Yeah, you're familiar with that, right? Anytime you have some kind of beauty pageant, right? When you say beauty pageant, okay, well, it's based on talent and whatnot, but let's just make life simple. Beauty pageant is based on beauty. All you can say is that the winner, Miss Universe, is more beautiful than the runner-up. And the runner-up is more beautiful than the second runner-up. But can you tell me how much of a difference? You can't quantify it. So that's all you can do. Okay. So that would be ordinal scale. Now, so in this case, even though you see numbers, don't think number, not numerical. Okay. So you can say nice is equal to 1, very nice is equal to 2. You can't say 2 minus 1. You can't do that. Now, let's go to something else. Now, let's look at the number scale. There are 3 more number scales. Interval and ratio. Okay? Interval, what can you do? You can take subtraction. You can take the difference, right? You can say that a room, which is 68 degrees Fahrenheit, is 3 degrees hotter than 65. Can you do that? Yes. So you can do subtract. Okay. You can also add, right? It's right now 65 degrees. Turn on the heater, it becomes 68. 65 plus 3. Yeah. So you can do both. Temperature. Now, can you do this? Can you say that a room that is 50 degrees Fahrenheit is half as warm as the room that's 100 degrees Fahrenheit? Can you do that? You can't. You know why? Because let's have 2 rooms, Fahrenheit and Celsius, right? If a Celsius, let's say 20 and 25. Okay? And this one is 32 plus 1.9, 1.8. Right? You know how to do conversion, right? You know how to do conversion, right? Okay. So you can say in this case that in Celsius, how much hotter is this? You can say this is 25% hotter, you think? Well, if you do it in Fahrenheit, it's 13% hotter. Why? They don't make sense. The reason they don't make sense is because they don't have the same zero. Okay? So there's no absolute zero. So you cannot do this kind of division if you don't have absolute zero. So in this case, with ratio scale, you can divide. You know, you can also multiply. Length, okay? Right? With length, you can say this is in inches, this is centimeter, right? And this is 5, this is 10, this is 2.54, right? Say, right? It's the same. So you can always divide because it has an absolute zero. Okay, be very wary of that. Why do I tell you to be very wary of that? You have to be very wary of that because most, let me say it again, most, if not all, machine learning and all of statistical method will work on numerical data. Okay, but the numerical data can be based on ratio scale, in which case it does make sense to make that kind of inference. It could be based on interval scale, in which case you can't compare ratio. So just because you end up with number, okay, basically your model is going to be something like this, x, and then f of x. Yeah, this is all your model is going to be, and this is going to be some number. But if your number is this, does this make sense? That's the question. If this is the number of whatever coins, number of tonnage, you can do this. But if this is your zip code, this is not a mathematical function. Okay? There has to be something that turns this into mathematical number that makes sense. And that is after halfway through the class, you understand what's called generalized embedding. Okay? With something like this kind of approach, okay, you can actually embed something like that, but not now. Okay, now you have to make the distinction. Okay, and again, let me say it again, even professional data scientists, working for corporation or startup, get this thing mixed up all the time. Unfortunately, it happens a lot, more than you think. Okay, so that's you guys. So let me shrink that, because I like to shrink things. Okay. Now, so that's it. That's your data. So we have to work with tabular data and something. And now something else. This something else means whatever. Instead of having something here, I have to put picture. You basically think of something that you cannot put in an Excel. Okay, I'm going to erase it. Think of items you cannot input in a spreadsheet. Okay. Now you can put picture here, but you won't be able to read it as a picture. Okay, you can just keep it. So it doesn't work. It doesn't work. It's something that you cannot enter here. What falls under this category? Well, I'm going to defer to that discussion because I'm going to discuss it under the heading of big data. So we'll come back to that. So think of the data. Now the population, this thing may not make so much sense to you, but there are two kind of way of populating. In other words, how do you get the numbers here? How do you get the numbers here? There are two ways. One is you record or you digitize from a pencil record. You can do that, right? You can go to an old record that's written in pencil and do OCR, optical character recognition, and then digitize it. Okay, whatever it is, all you're doing is just copying and storing. But there are different kind of data. There's a data that's actually generated. Okay. Now, most of the time when we talk about generated, we're talking about generated by a computer. For example, something like this. Random number generator. Yeah, I just generate number 14041. Let's generate it again. I get a different number, 127, whatever. Okay, this is a number generated by computer. You can also generate number by a coin toss. A lottery use ping pong ball. Have you seen that? They use ping pong ball to generate. So that's generated number. So you call that data as well. But let me say this. In our class, we are going to analyze this guy. Yeah? This thing in the way it can be used to help this job. But this is your job. Your job is really here. Data analytics mostly deal with data that is recorded, a real data that came from somewhere else outside the computer. Okay. So this is important for data scientists to recognize, but for your class, just don't have to pay too much attention because your data will come from somewhere else. And you can assume that that comes from physical recording, comes from things like that. It's not a generated data, it's a real data that pertains to real population. Now, the fun bit, big data. When you put in, well, let's do this. Let's do a Google search. Big data, let's see what definition. Okay. It has all kinds of stuff. Definition, it gets silly. It's very hyped up thing. But I'm gonna stick to the, well, shall we say classical? First of all, there are two things when we're talking about big data. Okay, when you hear the word big data, you have to realize there are two things we're talking about. One is the phenomena itself, phenomena of big data, meaning how come we have big data? How come 200 years ago we didn't have big data? There's the requirement that makes that to deal with big data. Well, now that we have big data, what are we going to do with it? And there's some kind of opportunity. Maybe we can do something with it. Okay. And then there's the data that's talking about technology or architectural platform. This is something that is not in this class. In fact, I try very much to remove the word big from this class title, except the name was already registered. But I try to use the word data analytics as the name of the course, because to study big data proper, presumably you are dealing with this as well, which you cannot do in a classroom setting. Okay, we are dealing with big data in this sense. And that sense has 3 V's. Now, nowadays we have 5 V's, 7 V's, but as far as I'm concerned, there's only 3 V's that we need to worry about. One, it's a velocity. Okay? Velocity means it comes to you fast. Not only does it come to you fast, you need to respond to it fast. Okay? Now, so in other words, there's the ingestion rate. It comes to you fast, but if you don't have to do anything with it, you can just wait, right? The data comes thick and fast, but you wait till the end of the day and then you just collect it. Well, a lot of big data has to do with response. It comes in big and fast, and you have to keep processing it really fast, almost like online or real time, and do some kind of response to latency. Okay? Now, these two things are very much technologically driven. Okay, so this will actually be answered a lot of time under here. You have to create a platform that infuse quick data, verify quickly, process it quickly, throw back the result quickly, almost on a real-time basis. Now, the big that you have to deal with, again, second B is volume, meaning it's a lot of them. So how are you going to store it? How are you going to process it? And this, again, is also something that has to be addressed with technological solutions. In this class, the primary focus of big data is on this bit. How do you deal with variety of data? In other words, you get a whole bunch of things that you cannot put in the Excel data. But somehow, before you analyze it, you have to put it into Excel format. Think of it that way, okay? You don't have to, you don't have to. But just think of it this way, that whatever model, it works off of rows of numbers. Okay? Rows of numbers, or row of symbol, or rows of, you know, designation. But you have pictures, you have videos, you have sound, you have connectivities, you have network response behavior, you have, you know, all kinds of weird things. You have internet traffic, computer codes, all of this you cannot put in an Excel file. So it's that variety that gave birth to this big data revolution. Okay? So think of this as requirement based. Okay, you need to deal with quick things. You need to be able to quickly deal with things. You need to be able to deal with lots of things. But the opportunity that came out is the fact that you can deal with a lot of different kinds of things. You used to just be able to deal with numbers. Now you can deal with pictures. Now you can deal with sound. You can deal with smell, chemical composition. Okay, genomic sequence, protein sequence, amino acid. That's the sequence of amino acid that makes a particular protein. These are all really crazy stuff. That is the big data that you should be interested in. The rest, these two things here, yes, it is important, but you can't deal with it because you're not an engineer. Okay? And you can't deal with it if you're a startup either, because you don't have money for big platform to deal with this, unless you pay for cloud service. Okay? If you want to have like sort of like on-prem or your own server, you need lots of investment. If you are a startup, you're not part of a big corporation, you don't have your own data infrastructure, data warehouse, you don't have your own data lake server to deal with it and so forth. You just have to pay for cloud service. Anyway, those are technological problems, but you know, I would deal with, I would just give you some word. And this is where, if you go to the class syllabus, remember I mentioned this book? This book is a very nice read that gives you a tour of what's involved. Okay, it's a handbook. It's not meant on the data. It's quite practical. It gives you a lot of understanding of the technology that is needed. So one of the things that you need is called map reduce. It's a very big thing. It's basically saying that instead of doing a job one at a time, which is what a computer does, you separate job into parallel tiny jobs. Okay, you map the job into a bunch of little jobs, right? Do it in parallel, and then you reduce that. So it's kind of like map reduce paradigm. So it has two things. It's distributed storage, which is good, because when you store your data in a distributed manner, if a local copy gets corrupted, you don't lose all the data, it's somewhere else. There's a distributed storage, a distributed processing. Distributed process, Hadoop data file storage, right? Or Hadoop, I keep messing this up. What does HDFS stand for? HDFS is Hadoop distributed file system. Okay. And there are many newer versions that improves on this. Distributed processing, okay, you have Hadoop, you have Spark, you have all kinds of stuff. Again, these are all the things that you cannot learn in school. And even if you learn it in engineering, like computer engineering school, chances are when you go work in the real system, it's going to have its own feature, its own particular operational manuals that you have to learn them again. Okay. So this bit is not the emphasis here. Okay? But certainly this thing, ability to deal with variety. Data that are not just numbers. That's quite a big deal. Having said that, a majority, again, of data science application that I see in life still does not take full advantage of this bit. It's still tabular data. Okay? So a lot of, you can say that this is a very exciting thing, V for variety. Okay, but in terms of application, there's still a lot to do here. Why? Well, because we've been recording numerical data for forever. Okay. Okay, so that's big data. Right. So that's what we mean by data. Now, what do I mean by analysis? Right? Well, let's talk about what it means by a model. What's a model, by the way, guys, in our sense? A model. Well, think of a fashion model. A fashion model is like a template, so you can display the clothes, right? That analogy doesn't work for us, for one thing. Unless you look like a model, chances are when you wear those clothes, you don't look like what you see when the models put them on, right? So this dress looks very nice on a professional catwalk model, but when you put it on, you don't get the same wow factor, right? Because that model, okay, does not represent general population. Okay. In our case, remember, what do we want to do? Remember what we want to do? We wish to analyze specific to make insight about general. So that fashion model is not very good, okay? Because he or she does not represent what normal people look like on the streets. Okay? The modeling we're talking about is something that looks like what you want to represent in real life. But in this case, you're not modeling the entities, you're modeling the relationship, the dynamics, the causation, the relation, and so forth. So, what are we trying to achieve with respect to modeling? We want to gain insight, some kind of informational advantage to solve problems, to find solutions. Now, how do you want it? How do you do that? Well, you have to build a model. What are the x's? If I knew x, what can I say about y? So these are really the sort of like questions you ask when you build the model. Okay. Now, by the way, a model is not just realistic. There's one thing that's very important. In fact, there are two aspects that's very important about a model. It's realistic, it's cheap, and it can be manipulated. Because most of the time, you don't want the model to just look like the real thing. You want it to behave like the real thing. So if you think about a toy model, like a car, a die-cast model, that looks like a real thing, but it doesn't behave like a real thing. That's also not a good analogy for us. Analogy for us, which is good, would be something like if we have a sand bucket. You know what a sand bucket is, right? Bucket of sand. And you pour water onto a sand bucket. And you see how water flows. And you say, that is a model of flooding. Okay, that's the model of flooding. Why is it cheap? So first of all, it is manipulatable. You can manipulate it. You can say, well, this is a sandbox. I'm going to pour water. I'm going to try to make a deep channel for water to escape. I can try that. I can try to make multiple different shallow channels for water to escape. I can try that and see which one is better, which one dissipates water faster. It can be manipulated and it's cheap because you can try different configurations. Now, why do you have that model? Because you cannot manipulate on a real system. Can you imagine if Gautama, right? Gautama wants to study flooding. Well, I want to know what flooding is going to do to the city. So I'm going to tear down all the streets, just make a big hole for water to run through. That's one experiment. A couple of months later, I tear down everything and I just make little channels of water to dissipate and see which one flows better. Can you do that with a real city? No, you cannot. It's expensive and nobody would, okay? So it has to be manipulatable and cheap so that you can study, you can optimize, you can work until you get the final solution until you're happy. Let's say the best solution is to dig one single tunnel very deeply so that the water can go through. Then you can say, okay, based on this model, this is how we're going to solve flooding problem for Bangkok. We're going to dig one big hole in the middle of the city that drains all the water from the rain. Okay, you've done all the experiments already. Okay, so that's what model does. Okay, now I'm just going to give you a name here. This is sort of like looking ahead, sort of preview where we're going. You know, where are the X's? If you're talking about distribution analysis, you know, like how tall are people? Okay, when do people die? Okay, you know, what is a typical age profile of people who severely suffer from COVID as opposed to people who just, you know, have no symptom. Okay, this would be something like distribution analysis, and this is where you use mostly statistical method. Mostly, rarely do you use machine learning. Okay, in special cases, you do what's called data mining. I will talk about that. So this is how you answer where are things, you know. So again, you're making inference on small group of people to make inference about big population. So you collect 3,000 COVID patients and you make inference about all the COVID patients. So this is kind of distribution analysis. Cluster analysis is not like where they are. It's sort of like, I don't care where they are. I just want to know if they're clustered into different groups. Yeah, you can imagine, right? I say, well, let's have a party. There's a big hall, maybe a wedding party or something. You can see that, oh, this group, everybody is everywhere in the middle. That would be like a concert hall. Or you can have something like class reunion, where you have a big group and you have a small group. Or you can have some kind of wedding with a very large families that has a very large social contact, but nobody knows anybody. So you have little pockets of people clumping together. Okay, they just sort of hang around the cocktail table, and there are 5, 6 of them, and they talk to each other all the time, but they don't talk to the other 5 or 6 people. So you want to know about this kind of clustering. Well, occasionally you use statistical method. Mostly, generally speaking, you talk about machine learning. Okay, so that's a sort of model we have. Now, that kind of models tells you about some attributes of the population. But the other kind of model is about inference with a direction, like an arrow. If I knew X, what can I tell about Y? If I knew somebody's weight and blood pressure and caloric intake and cholesterol level, can I predict probability of heart-related disease? I'm going to study it based on 300 people, but I'm going to infer that to the general population. So that's a like X to Y thing. And here we have two kinds of problems. Think of it as two kinds of output here. So these are all your X's. These are all your X's. And this is a Y. If your Y is numerical, it's a regression problem. If your Y is some kind of label, some kind of ordinal, so if your Y, let's go back to here. Let's go back to here. Let's go back to here. Remember the number scale? If your Y is descriptive or categorical, it's usually a classification problem. If your target, your Y, is a quantitative or numerical, then it is classification. So regression analysis is traditionally done using statistical method. More and more it's using machine learning. More and more. Classification analysis used to be, but now it's primarily, used to be statistical method, used to be the norm. Once, emphasis on once, not anymore. Now it's primarily learning. And again, data mining comes in a special case. Okay. Now, I would finish by saying that when you solve a problem, you kind of like tend to do a little bit of model inversion. Once you understand that this X leads to Y, chances are you want to invert that information. If I want this Y, what X do I get? You see what I mean? So it tends to be something, like for example, you understand what X's is a risk factor for heart disease, right? But your objective really is not just to study from risk factor to heart disease. You want to go the other way around, from reducing the risk of heart disease into what risk factor can we manage. So we go from left to right, this kind of behavior, sleeping in bed and eating Doritos and not exercising and staying up late, blah, 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 lead to high risk of heart disease. Okay, you want to invert that, some kind of model inversion. Okay, you want to invert the mapping. You want to go, which X would give you the Y that you like, right? You want people to be healthy, right? So what's the inverse of that? Inverse is to be healthy, you have to exercise, drink a lot of water, blah, blah, blah. So you do a lot of that. You do a lot of that. Okay. So let me do this. Okay. Now, a particular case is what's called optimization. It's not only, which X will give you that Y that you want. It's really, I want the best Y, the best possible Y. Give me the best X combination of X that will give you the best possible Y. And remember I told you about operations research? Well, the X is the location of radar station in the World War II in the southeastern coast, across the English Channel. Okay, where should you put the radar station? The best solution, the Y, is the maximum coverage. Best improved performance or something like that outcome. So you do model inversion, but you kind of like, you're really ambitious. You want to get the best Y. Okay. Which X will give you the best possible Y. Okay. So, which placement placement of radar station would maximize the coverage of enemy fighter coming over the English Channel. Right? And that is historically the operations research problem. I love this. It's like the movie Enigma, where you have historical story behind the mathematics. And then there is finally, I'm just going to finish with this optimal control model. This is a little bit tricky. It's about controlling the trajectory. You're not trying to get the best thing, maximum thing. It's like when you're controlling a flight. You're not trying to say, what should I do to make the airplane go highest? Or go to the rightmost, go to the leftmost. No, you want to say, what can I do to make the airplane fly in a narrow corridor? Okay, and this is what central bankers, and I'm from central bank, okay? This is what central bank do. What can I do to the economy to make the economy grow, not so fast, not so slow, but at a sustainable pace? Stable and sustainable. So the Bank of Thailand does not want the economy to grow as fast as it could. It does not want the economy to shrink. It wants the economy to grow sustainably and stably. So this is a very tricky problem. It's not a single target you want, but it's sort of behavior. This is called optimal control. Now this is related to reinforcement learning. But you're not going to deal with this very much. So in this class, no, not so much. Here as well, not so much. In this class, you're going to do a lot of this. Okay. In this diagram, I'm not, I haven't put the asterisk to say this is the emphasis of this class because I'm making this mind map for a general purpose. Okay. So pay attention to my work when I say, okay, not so much attention on this, not so much attention on this, but a little bit more attention on this part. Okay, so that's for you to remember. Okay, so right. So now we are, I guess, out of time, and I would go over a little bit of this at the beginning of next class, but mainly I'll start moving into the mathematics. Now I don't know how well you guys know each other, but at some point we're going to have to put people in groups. Okay, now. Those of you who are not of the right spirits are already scared of learning will probably be dropping out. But if not, working on the assumption of 48 students, okay, we can have like 6 groups of 8 students. I don't know how well you know each other, but what I would like to do is mix and match a little bit. So maybe one time we'll have group assignment based on random assignment. One time based on your own picking up. Okay, so maybe I would start with random grouping, and once you know each other more, maybe you can sort of like pick and choose your friends or whatever. Okay, right? Okay, so I think with that, I think we are pretty good. So let's call it a day, and I would try to think of a microphone thing. Yeah, I can. It's just today, whatever it is, I would order it online now. I don't want to go shopping on pen paper. Just like that. I don't want to do that. Okay. So with that, I think we done for the day. Yes, we have a hand. Yeah, I happen to glance over. Come on.
Will we get this recording?
Yes, we will. Yes, we will. Peanut has to record it and send me the link, and I'll upload it just like this class. Yeah. So this is last year. So it's all uploaded. Okay. So this year you will upload it as well. I'll upload it as well. So there'll be a playlist of Basai Data Analytics Autumn 2021. Okay. I adjust the material a little bit from last year. So you can go ahead and look through that. I don't know if the voice recording is a little bit better because half the classes or most of the classes from 2020 was conducted in a classroom with a microphone, sort of. The IT team has a camera and microphone, so I don't know if recording comes up better. Okay, so we have to work around. We have to work around the limitation. So it's going to be recorded here. Okay, ครับนะ